This is lecture 10. So in last lectures, we have discussed different modeling techniques. One is that state space, one is that transfer function modeling, and we have also discussed the block diagram representation, and from block diagram how to represent a dynamical system in signal flow graph. We have also discussed in detail. And from signal flow graph how to find transfer function from one variable to other variable using Mason's gain formula. We have discussed in detail with some examples. So today we will be discussing another modeling technique, that is that state space method. So this is that modeling in state space. So first let us see what are state variables. So this is actually the smallest set of variables that completely determines the behavior of the dynamical system for any time t, suppose t greater than t0, with the knowledge of these variables at t equal to t0 together with the information of the input for t greater or equal to t0. So that means this is the smallest set of variables, and if we know the values of those variables at t equal to t0, and if we have that information about that input t greater than t0, then we'll be able to describe the dynamical system. So this is the smallest set of variables. So let us see what is state variables. So state variables, so the smallest, so this is very important, that smallest, because we can take a number of variables, they may not be the smallest set, so then that set is not the state variable set. So the smallest set of variables that completely that means we can find what to be its outputs, what are the other variables involved in that particular system, and what are the initial conditions, etc. Everything we can have from the set of variables. So completely determines the behavior of the dynamical systems for any time t greater equal to t0 with the knowledge of these variables at t equal to t0. That means if we know what are the values of those variables at t equal to t0 together with the information of the input t greater or equal to t0. So that is very important. That means what is called state variables. So state variables is actually the smallest set of variables that completely determines. So this is also important. That means if you partially describe that system, it is not that state variables. It completely determines the behavior of the dynamical system for any time t greater or equal to t0 with the knowledge of these variables at t equal to t0 together with the information of the input for t equal to t0. So this is actually called that state variables. So what is modeling in state space? So that means whenever a dynamical system is given, first we need to identify which one is the minimum set of variables that can describe that system. So that means those are the state variables. So first we need to identify which are the state variables, and then we will be following some technique uh, by which the dynamical systems can be represented in state space form. So that state space form is actually in matrix form that we'll see today. So there are some important points, important attributes involved in the state space modeling. So these are actually as follows. The concept of state is not limited to only physical system. It is also applicable to biological systems, social systems, economics. So state variables need not to be physically measurable or observable quantities. And uh, there are some important aspects of this mathematical modeling technique, because in transfer function based modeling we have seen whenever we describe a system using transfer function, just by looking at the denominator degree we can say what is the order of that system. So here the number of state variables is the order of that system. Those things we will see via some numerical examples. Then I think we'll better understand that what are the important aspects of state variable modeling technique. So let us first point out a few important facts about that state space modeling. So that is the concept of state is not limited to only physical systems. It is also applicable to so from here you can see that means to find a mathematical model of any social system or economics, you can also use state space modeling technique. It is also applicable to biological systems, economics, social systems, etc. So you may think of like that state variables means always it should be the physical quantity. It is not. That means the state variables need not to be physically measurable or observable quantities. Need not to be. We will see all of those things by some numerical example, then those points would be clear. physically measurable or observable quantities. So now what we have seen that the definition of state variables, which is very important, and as I have pointed out, the smallest set. So if anyone asks you what you mean by state variables, so you need to mention that this is that smallest set of variables that can completely determine the behavior of the dynamical system. And we have seen that the state variable technique is applicable to physical, not only to physical system, but also the other systems like biological systems, economic, social science. And state variables always need not to be that physical, measurable, and observable quantities. So now let us see what is state vector. State vector. If n number of state variables are needed, then these n state variables are considered as the n components of a vector x. This vector is called the state vector. So suppose if n state variables are needed to describe the dynamical systems completely, then these n state variables are considered as the n components of a vector x. So this vector is called state vector. So that means if you have n number of state variables, and if you write those state variables in vector form, that is called a state vector. So that means if x is that state vector, and if you have that n number of state variables, so these are the state variables. So this x is called that state vector. Now what is state space? So from here it is clear that, so suppose you have n number of state variables. So now the n-dimensional state space whose coordinate axes are x1 axis, x2 axis, xn axis, like that. That means if you have suppose two state variables, and if you consider the two-dimensional space where in one axis one state variable is one axis is denoted by one state variable and other axis is denoted by other state variable in this two-dimensional case. So now the state space here, it is the two-dimensional state space. So here what is that state space? What is the state space? The n-dimensional space. So that means in case of n number of state variables, the n-dimensional space whose coordinate axis are x1 axis. That means each axis is represented by one state variable, x2 axis, and so on. So you have xn axis is called a state space. So if you have n number of state variables, so it is n dimensional state space. So now we'll see one example. So let us take one simple third order differential equation. So suppose a dynamical system is represented by these particular dynamical systems. So suppose a dynamical system is represented by this dynamical system where input is ut and output here we are defining that output is yt, which is defined as suppose x1t. So now just look at here how to define state variables. So this is the technique we follow in state space modeling. So here that output is x1t. So now I can define another variable that is x2t, which is actually the derivative of the first state variable x1t. So this is nothing but that dyt by dt, and again we will define another state variable that is x3t, that is dx2 dt by dt. So that means that would be d2 yt by dt2. So now we can represent this dynamical system in the form of these three state variables x1t, x2t and x3t. So you may ask, how do we know, that means how many state variables are required to represent this dynamical system? Yes, that is very important. So basically this particular number states you how many state variables you need to describe this dynamical system. So that means the order of the differential equation would be equal to the number of state variables. That means minimum number of variables you need to describe this dynamical equation. So let us write. So here you see that order equal to 3. So that is actually the order of the differential equations. So that means it indicates you need 3 state variables. 3 state variables are required to describe this particular system. So this is a very important fact in state space modeling. So as I have pointed out, so before getting the model of that dynamical system in state space framework, you need to identify how many variables are needed or how many state variables are needed to completely describe that system. Whenever the system is described in dynamical equation form, just by looking at the degree order of that dynamical equation, you can decide how many state variables are needed. Then you need to follow this technique. So suppose that output is one state variable, then you define the other two state variables in that way. So now if you represent this dynamical system, so how it looks like, here you can see. So x3t is equal to d2y by dt2. So then for this particular dynamical equation, I can write that x3 dot. So x3 dot means d x3 by d dt means, so if we just write here dx3 by dt, so this is nothing but d3y by dt3, which is this term and that term, they are same. So here we can just write, that x3 dot, so this equation we are writing, then I am taking the other terms, so those terms on the right hand side, so that is minus 9. And now you look at here d2y by dt2, so d2y by dt2 is nothing but x3t, that is x3t. So then minus 26 dy by dt, so dy by dt is equal to x2t. Now minus 24 this term, yt equal to what? Yt equal to x1t, and this term you have, that is 24 ut. So now you can write these equations like that. So what is x2 dot t? So x2 dot t, here you can see x2 dot t is equal to x3t, and what is x1 dot t? So x1 dot t is equal to x2. So that means you have three state variables, and we have written three dynamical equations, differential equations, first order differential equation, that is x1 dot t, x2 dot t, and x3 dot t. So now next step is we need to represent these dynamical equations in matrix form. How we can do it? So if we write this one, x3 dot t, x2 dot t, and x1 dot t, so then here you have x3t, x2t, and x1t. So now we can see here that minus 9, then minus 26, then minus 24, and here you have another matrix term, matrix, here you have 24. So the first equation is written in matrix form. The second one you can see here, this one, so x2 dot equal to x3t, so that means you have 1 here, rest of the terms are 0, and this one x1 dot t equal to x2t, so you have 1 here, this is 0. So this is actually the representation of this particular dynamical system, in terms of the state variables. So three state variables are there, x1, x2, and x3, and one thing is left, that is this equation. This equation we have not represented yet, that is, what is that? Output. So output equal to yt equal to x1t, you can see here, and we have defined like this. So now you can write that yt, that is that output, equal to, again you need to represent it in matrix form. So three state variables are there, x3t, x2t, and x1t. So then that would be, and here you have 0 into ut, because that output is not directly related with that ut. So here you can see that yt equal to x1t, so that can be represented in matrix form 1. So this particular structure, so this one and that one, they are called that state space modeling of this dynamical system. So that means whenever a dynamical system is described by one differential equation just by defining three state variables, and here I have shown how to define state variables and how to choose the number of state variables. So the number of state variables is dictated by the order of the differential equation. So here that order is 3, this order is 3. So that's why you need 3 state variables to describe that system. And just by defining state variables and following this particular technique, you can represent that differential equation in matrix form. Now you may ask a question, that means here I have followed this sequence x3, x2, x1. So can we just change that sequence? That means if I write x1, x2 dot, x3 dot, or x2 dot, x3 dot, x1 dot. So is it correct? Yes, it is correct. So any sequence you can follow, because later on you will see that the state space modeling is not unique. That means for a same dynamical system, you can have infinite number of state space modeling. So the state space modeling is not unique, and here you can follow any sequence, maybe x3, x2, x1, or x1, x2, x3, or x2, x3, x1, whatever sequence you can follow. So this is actually the technique we need to follow for representing a dynamical systems in state space framework. So let us see, that means how this particular modeling is related with the transfer function based modeling. So for this particular dynamical systems, so let us write it again. So here that is d3y plus 9 d2y 26 dy by dt plus 24 yt plus 24 ut. So here we are interested in what is the transfer function. So what is its transfer function? What is the transfer function of the system? So what is the transfer function of the system? So we have seen two modelings. One is this one, that means the system is described in differential equation form. We have seen another one, that means it can be represented in state space form. The third one, we are just looking for the transfer function based modeling. So here, for getting the transfer function of that system, so we need to take the Laplace transform. So if we take Laplace transform, taking all initial conditions 0, as you know, for finding transfer function we need to take all initial conditions 0. So if we take the Laplace transform, here we can write that taking Laplace transform, we get, so here s cube small s cube, then ys, then 9s square ys, 26s ys plus 24 ys, and then 24 us. Here just I am writing all initial conditions are 0, all initial conditions are 0, because in case of transfer function based modeling, we need to consider that all all initial conditions should be equal to 0. We have discussed it already. So then if you take y common here, so if you take y common, you can write this particular algebraic equation in this form, that is 24 divided by s cube plus 9s square plus 26s plus 24. So this is the transfer function you have for this particular system. And now you can see that what is the order of the system. So order of the system is this 3, the maximum degree of the denominator. So order here you can see this is a third order system. This is a third order system. So I think from this simple example you can understand that whenever a dynamical system is represented by a differential equation, the order of the differential equation actually tells you how many state variables you need to describe these systems completely. So we need 3 state variables, and this technique we have discussed, that means how to represent that system in state variable form. And then again we have seen, if we are interested in to find what would be the transfer function, just by taking Laplace transform and taking all initial conditions are equal to 0, we can have a transfer function of that systems. And here also we can see that the order of the system is third order. So let us take one more example, because from those examples we'll learn how to represent that system in state space modeling framework. So let us take one physical example, spring mass damper systems. So another example here. So we assume that this is frictionless, and we have two masses here, mass 1 and mass 2. Mass 1 and mass 2, they are connected via a spring. It's a linear spring we have considered, and here the displacement is x1, displacement is x2, and here one damper is connected. And if you apply that force Ft here, then what would be the dynamical equation and how we can represent the dynamical equation in state space form. So this is our objective. So this is frictionless, and here this is that damper. So damper coefficient is D. So now I think you all know how to represent this particular system in dynamical equations. So I'm just writing directly. If you have some problem in understanding the dynamical equations, I suggest you to see your first year class notes, that mechanics. And here for the first mass, the dynamical equation would be m1 d2 x1t by dt2, then d, the damper, the damping force directly proportional to that velocity here, and this is that spring, the force due to that spring. So this is that first equation. You can draw the free body diagram, and from there directly you can write it. Then for the other mass, this is the dynamical equation. Equal to the applied force. So now you can see that. So if you have one physical systems like that, two masses, one spring and one damper, you can represent it just by writing two differential equation. So now Our objective is to represent this particular system in state space form. So you just look at here, as you have two differential equations, and then we need to understand that how many state variables we need to describe this particular system. So one important thing is we need to first understand that as the dynamical system is described by two differential equations, so these two differential equations are independent. So differential equations are independent. Independent means, those coefficients are not just the factors, multiplication factors. Like if you have one differential equation, say 2 dy by dt equal to suppose 5. Now if you multiply with 3, so then another one would be 6 dy by dt equal to 15. So that means these two differential equations, they are actually linearly dependent. So in this case, first you need to see whether the differential equations are linearly independent or not. So in this case, they are linearly independent. You can see here, if you look at the structure of the dynamical equations, then you can see these two differential equations are linearly independent. And then you look at the order of the each differential equations. So this order is 2, and here this order is 2. So that means whenever you have more than one differential equations that are describing the dynamical system, first step is to see whether the differential equations are independent or not. If independent, then just look at the order of the differential equation. So here you have 2, here you have 2. So now the number of state variables required to represent the dynamical system is equal to the sum of these orders. So that means here I can write that two differential equations. This is very important, that two independent. This is very important, independent. Two independent differential equations. So order of the system, as you know, the order of the system is equal to the number of state variables you need to describe that system. So is equal to sum of the order of the differential equations. So in this case, you have 2 plus 2, that is 4. So number of state variables you need to describe this system equal to 4. So let me describe it again. So whenever a dynamical system is described by a set of differential equations, you need to first see whether the differential equations are linearly independent or not. So suppose three differential equations you have, two of them are linearly dependent and other one linearly independent. So just you take the set of linearly independent differential equations, and then you see the order of the system is equal to the sum of the order of the differential equations. So in this particular example, the orders are 2 and 2, so that is 2 plus 2, that is 4. So the number of state variables required to represent that system is equal to 4. So now first step we have done. The second thing is how do we represent that system in state space. So here you have that displacement, that x1, and for mass 2 you have another displacement, that is x2. So that position x1 and position x2. So now we define the other two state variables, that is the derivative of those displacement, that is that velocity. So let v1, that is the velocity, is equal to dx1 by dt, and v2 equal to dx2 by dt. So take these two variables as state variables, v1 and v2. So now for the first state variable, so here you can see that dx1 by dt, so v1 equal to dx1 by dt. So now if you take dv1 by dt, so that means if you take dv1 by dt, that would be actually d2 x1 by dt2. So here you can see that d2 x1 by dt2. So the first equation is represented as dv1 by dt. So divide this whole differential equation by m1. So you will get that minus d by m1 v1, then k by m1 x1 plus k by m1 x2. Here you can see that dx1 by dt equal to, already we have defined that dx1 by dt equal to v1, so that would be dv1. Here you can see, and if you take it on the right hand side, that would be minus dv1. So here you can see that minus dv1, and if you divide the whole terms by m1, that would be minus d by m1 v1. Similarly for the other term, you can see here that kx1, and here we have written that minus kx1 divided by m1, and the other term is this thing. Similarly, the other equation can be represented as that dv2 by dt equal to minus k by m2 x2 by k by m2 x1 plus 1 by m2 ft. So ft is that applied force. So now we have two equations here, and you can see that this is third equation, this is fourth equation. So we have four first order differential equations. So these are all state equations. So now our objective is to write those four equations in matrix form. So if we write it in matrix form, so we have the dv1 by dt. Again, I want to emphasize that you can follow any order. So here just I am writing the dv1 by dt, then dv2 by dt. So these all are actually that first order differential equation. So in state space, on the left hand side, you have only that first order differential equation term, dx2 by dt. So you have four state variables, and this is that first order derivative of those state variables. So now I am writing it in state space form. So dv1 dt. So here obviously you have that state vector. So state vector is v1, then v2, then x1 and x2. So this is that state vector. And what is your input? So input we have only ft. So now let us see how to represent it in matrix form. So dv1 dt, that is v1, so minus d by m1, so this term, then v2, so there is no v2 term, this one, and then this term, that is minus k by m1, and the last term is k by m1. There is no input, so 0 here, and for this one, that is minus k by m2, here this term, and that is k by m2, this term, and here you have by m2 this term, the other two terms 0. Similarly, what is dx1 by dt? So dx1 by dt equal to v1, so that means here you put 1 and all three terms are zeros. And similarly, what is dx2? So dx2 equal to v2, so dx2 equal to v2, so here you put 1 and other terms are 0. So this is actually that state space modeling. And if you say that, okay, we are interested in to find what would be the output. So if we consider that x2 is that output, then we can easily represent that x2, that is that output equation. So x2 equal to, you have that state vectors v1, v2, x1, x2. So this is that state vector, and output equal to x2. So that means all are 0. Here you have that 1. So this is that state space model of this particular dynamical system. So now you have seen that means how to represent that system in state space form. So now, so here what important things we have noticed. One thing is this particular dynamical system is represented by two differential equations, and we found that these two differential equations are linearly independent. Then we have observed what are the orders of the differential equation. So if we take the sum of those orders, so it tells you how many state variables you need to describe this one. So here in this case it is 4, and the order of that system is also 4. Then we have defined the state variables. So two state variables are the position x1 and x2. The other two state variables are the velocity v1 and v2. Then we have written it in matrix form, and this is that state space modeling. So now we are interested in to see another important concept in state space modeling, that is the state space modeling is not unique. So you can have infinite number of state space model for a given dynamical system. So let us see how to do that one. And this is very important, because if I give you one dynamical system and ask you to find the differential equation, suppose in this class you have 270 students, so you can have 270 different state space equations, because they are not unique. But interestingly, they all are same. That means if you take the transfer function, if you find the transfer functions of that system, you will see that all the state space equations are describing the same dynamical system. So that thing we will see by this particular example. So it is very important. So from this example, we'll learn that state space is not unique. So let us take one, already we have taken one mechanical example. Now let us take one electrical example. So take a simple circuit. Simple circuit, so two resistors are there, and you have two capacitors. There is no voltage source, so basically there are some initial charges. So suppose the capacitance is C, and it is some initial charges Q1 and Q2, and this is that resistance R. Suppose that current what is flowing, that is I1, and here that current is flowing I2. So now you just apply that KVL. So I'm just writing directly here. You can see for the first loop, for this particular loop, so this loop, if you see this loop, so I'm writing that KVL, that is Q1 by C, that plus minus, then current is flowing along the direction, that is plus minus, so this is I1 R, and then here if you traverse along this direction minus plus, so that is minus, that is q2 by c equal to 0. So this is that first KVL, and if you just see this particular loop, what will you get? That q2 c, that is plus minus, and it is again for current is flowing along that direction, so that is I2 into R equal to 0. So you have two KVL equations, and from here another relationship you can have, that is current, this current I1. So current I1 equal to dq1 by dt, that is q1 dot, and another thing is that I2 minus I1. So if you just look at this particular node, so I2 minus I1, so here this is I2 and this is I1, and there will be some current here, so that is equal to dq2 by dt equal to q2 dot. So then you can write from here, that is I2 equal to I1 plus q2 dot. So I1 equal to q1 dot, so that means if you replace it here, you will get q1 dot plus q2 dot. So those relationships we can have from this particular circuit. Then let us write the state equation. So from first equation, here you can see this is that first equation, and in place of I1, I will be just putting q1 dot. So then if I write it here, so what I will get, that is R q1 dot, you can see it here, this term R q1 dot, then I am taking this term on the right hand side, this term on the right hand side, so that means minus q1 by c and plus q2 by c. So this one equal to minus 1 by c q1 plus 1 by c q2. So we have this first equation. And what is that second equation? Second equation you can see here, I2 here, I2R equal to minus q2 by c, and here you can see this I2 equal to q1 dot plus q2 dot. So you can write it here, that R q1 dot plus q2 dot equal to minus 1 by c q2, the second equation. So then if you write it in matrix form, what will you get? So I am writing it in matrix form. So on the left hand side I have q1 dash, q1 dot and q2 dot, that means first derivative of q1 and q2, and then the right hand side we can write it in matrix form, that is q1 q2, and here you can see that minus 1 by c plus 1 by c, then minus 1 by c 0, and here the first one is this one and the second one is this one, you can see here. So these two equations are written in matrix form. So now what is q1 dot and q2 dot? So q1 dot and q2 dot, just apply matrix algebra. Q1 dot and q2 dot, if you multiply the inverse of this matrix from left hand side, so then you have R 0 R inverse minus 1 by c 0 minus 1 by c q1 and q2. So then what we can see, first we need to find what is the inverse of this matrix. So as you know, I think all of you know it, the inverse of this matrix, again I am just finding it here, the inverse of this matrix is R0 RR. So that is, find the determinant, that is R square, and if you find that adjoint, that would be R minus R This is transpose. If you forget that inverse of a matrix, please see some linear algebra book, and then you will get 1 by r 0 minus 1 by r 1 by r. So this is that inverse of this matrix. So now if you replace this one here and if you multiply it, then the final expression that you would have, that is q1 dash, not dash, the derivative of first derivative of q1 and q2 is equal to, so just replace it, just replace this one here, that is the inverse of that matrix, and multiply, then you will get minus 1 by cr, 1 by cr, then 1 by cr minus 2 by cr, q1 q2. So now you can see that this is that state space model of this particular circuit. This is that state space model, this particular circuit, where the state variables, we have taken the state variables are q1 and q2, the charges stored in the capacitor, and we can have this state space model. So now interestingly, we can also describe that circuit. So here we can write it here. We have describe the circuit, in terms of q1 and q2, the charges stored in that capacitor. So now we can also describe this circuit in other ways. So describe the circuit in terms of I1 and I2. You can also represent it in terms of I1 and I2. So let us see how. So we have those dynamical equations, these dynamical equations. So again I am writing those things. So here only one thing is that we have represented it in this form, that is 1 by c dq1 by dt plus r di1 dt by 1 by c dq2 by dt equal to 0. Just look at here the dynamical equation that we have. The first dynamical equation here, if we take the derivative, of this one, so basically that would be 1 by c dq 1 by dt plus r into di1 by dt minus 1 by c dq2 by dt. So that equation I have written here just by taking derivative. Similarly for other equation, here this equation, if we take derivative, that is di2 by dt into r plus dq2 by dt into 1 by c. So that means if we just take the derivative of that, so we have that 1 by c dq2 by dt plus r di2 by dt, that is equal to 0. So now we can see here that dq by dt, we can see here what is dq by dt. So dq by dt is nothing but I1 Similarly, here what is dq2 by dt? You can see in the circuit here that dq by dt, the dq by dt, that is I2 minus I1, because the current what is flowing here and flowing here. So I2, here I can write that I2 is equal to I1 plus dq2 by dt. So that means dq2 by dt is equal to I2 minus I1. Here dq2 by dt equal to I2 minus I1. So that is I2 minus I1. So now we will just write these equations here. We keep this term the left, that is r di1 by dt, and if you just divide this r, these equations by r, so then you can have di1 by dt equal to minus 1 by cr, the first term. In place of dq1 by dt I am writing I1, and the second one here, that would be 1 by cr, because you are dividing these whole terms by r. And what is dq2 by dt? dq2 by dt, we have seen that this is I2 minus I1. So if you just simplify it, you will get that minus 2 by RC I1 plus 1 by RC I2. So similarly, the other one, that is di2 by dt, that is equal to 1 by CR or 1 by RC into, we are taking this term to the right, so that means this minus would be plus, that is I1 minus 1 by RC I2. So you have now two differential equations in terms of I1 and I2. So now easily we can represent these two differential equations in matrix form. So if you just represent it in matrix form, so you have di1 by dt, di2 by dt, that is 2 by RC, 1 by RC, 1 by RC minus 1 by RC here, and this is that new state vector, that is I1 and I2. So as it is I1 and I2, then you can see here